Hi, good afternoon, everyone. Hello. Hi. Uh, first of all, hopefully you already saw my announcement. So exam two has been delayed for postponed for 1 week. Hopefully that should give you enough time to prepare for it. But that doesn't change the coverage of exam two. So it still covers all the lectures in section number two. So even though we're going to squeeze in 2 lectures from section 3, but those won't show up in your exam number 2. Last time we talked about base excitation, and we learned how to use Laplace transform and Bode plot to analyze dynamic systems. So in the end of the previous lecture, I give you a car seat problem. So assuming that there is a passenger together with a seat sitting on a mount. So we have the freedom to design the mount stiffness and also the damping ratio of the mount. And assuming that there is a car which has a really rigid tire, this car is driving on a really bumpy road, and we assume the road profile is a cosine function with a constant amplitude y0. Okay, so our target is trying to minimize the acceleration experienced by the passenger. In other words, you want the passenger to have a very smooth drive. There's another way to say it is you want your m x double dot to be minimized. Your mx double dot is the inertial force experienced by the passenger. So either way, we want to improve the comfortness of the passenger. So we have the freedom to choose K and C. So how should we design the K and C? So we want to use Laplace transform. And then in order to use Laplace transform, we need to use transfer function. In order to get transfer function, you need to identify your output, and you need to identify your input. So in this case, we know your input is going to be your base displacement, because that's why the passenger is going to experience vibrations. The output is going to be x double dot or mx double dot, either the acceleration or initial or inertial force. So to simplify our discussion, we focus on the second one. The benefits of adding a m in front is that eventually the transfer function can be unionless if you add an m in front. So that means we want to calculate m x double dot over y, right? So that's our transfer function. We want to minimize the amplitude or magnitude of transfer function. Let me simplify it, because in some textbooks they usually use t dot tf. That stands for transfer function. All right, so in order to find your transfer function, you have to go back to your ODEs. For base excitation, the ODE, we already derived that. I'm just going to copy from previous lecture notes. Okay, so that's your system dynamics. So we need to find, so most of the students actually got confused about these mx dot in the transfer function. Let's name or define at equals to x double dot t. We use another symbol to define your acceleration, so then we can avoid confusion. So that means we want to find out m times as over ys, right? That's your transfer function of interest. So you can easily apply this chain rule, m times as over xs times xs ys. So insert a xs term to both the numerator and the denominator, then you can actually convert your transfer function into two parts. So you can see that the second part in this case is your displacement transmissibility. We already derived that in previous lectures. And then the first one is it's like a coupling. So we can get these transfer function from these definition. So what you do is you do Laplace transform on both sides. Your AT becomes AS, right? And then your X double dot gives you S square times XS. So that gives you AS over XS times M equals to MS squared. Oops. Yes, MS squared. Yep. So that's the relationship we got. So that's the first term. The second term is the displacement transmissibility. So eventually your force transmissibility, or M times AS over YS, equals to the first term times your displacement transmissibility. So that's the transfer function you're going to get. And then after that, we define a relative frequency or frequency ratio. So this is your driving frequency over the undamped natural frequency. After this definition, you can calculate the force transmissibility and convert it to a unitless transfer function. So this is the magnitude. And if you look at the plot, I actually provide you the MATLAB code online. So this plot changes as you change the damping ratio of your system, okay? So in order to minimize acceleration or inertial force, if you look at here, so the best line, the line of operation, should follow the red line, right? So then we can look at two different regions. On the left-hand side, let's name it as low frequency, low omega. That's your high omega. So for low frequency, for low omega, in order to follow that red line, you actually want a high damping. But then for high frequency, you want low damping. So that means to minimize the vibration on a car seat, sometimes you need high damping, sometimes you need low damping. So that's why in section number 5, we're going to learn active vibration control. So for some of the high-end cars, they actually have tunable dampers. You can change the damping according to the vibration the car experience. So what the function is, in traditional cars, what they do is they have a dashpot like this, right? So that's a connector. That's a connector. So inside of this dashboard, there is basically the cylinder. And then inside of the cylinder is filled with damping oil. It's really very high viscous oils. And then as it vibrates, so this thing is going to give you a damping C. So what we do is, in some of the cars, what they do is, besides of these damping oil, they also put small soft magnetic particles, for example, iron particles. And then on the outside of these cylinder, they will get a coil. And then they would apply the current of voltage through the coil. So there are two cases. When no current is applied, then your particles will be suspended, will be distributed uniformly in the dashboard. So in that case, when you have no voltage, in that case you have low damping. But once you have, if you have some voltage, then that's going to generate a magnetic field. I'm going to draw these flux lines. These flux lines is like when you go back to your high school physics class, if you put some iron powders next to the permanent magnets, those powders will be oriented by the flux, and then you're going to see some flux lines around the magnets. That's going to be the same thing in these dashboard design. So what you're going to see is you're going to still have the damping oil, but then inside of this damper, these particles will be aligned. It's equivalent that it's equivalent to add fibers in your damping fluid. So in this case, your damping coefficient will be increased. So that's why it gives you high damping. So for some of the expensive cars, I don't know which, actually I don't know which car actually have that. Perhaps some of the Audi or Benz, they might have this kind of dashboard. So this dashboard is definitely, it needs more, so it actually needs more energy because you have to apply the current to drive the dashboard, and then it needs more maintenance because the iron particles over time, they're going to settle, they can agglomerate, and then you have to more constantly replace the damping oil. But just give you an idea. So this explains why some cars are expensive, some cars are cheap. If you look at these transfer function, you have to make sure you have to make some of the components active in order to form these red lines specifically. All right. So let me see anything else. Okay, so that's how we design damping C, right? How do we design C? You want a large C value when at low frequency. You want a smaller C value at high frequency. So how about K? So when you design K, you always remember that K and M together, they're gonna determine your natural frequency, okay? In this case, you want your omega over omega Rn, which is your frequency ratio. You want these to be small, right? Once your R is small, then you always work on this left area. So this area usually have a less magnitude compared to the high frequency. So you actually want a low R value. So if your omega is fixed, then you want your omega n to be large. So if you have a constant m, that means you want your K to be as stiff as possible. So in this case, and also, you can also discuss the mass of the passenger. So as you can see here, if the passenger is heavier, it actually reduces the omega n, and thus we're operating further close to the high frequency range. So that means a lighter passenger is going to have a better customer experience compared to heavy passenger. So that gives you another reason to keep fit. All right. So that concludes the base excitation. I'm gonna give you an example, which is homework number, which one should I use? Yeah, let me use homework number 1. So there is a machine. We already know the total mass or total gravity, total weight of the machine is 20,000, 2,000 Newton. It's sitting on a system, sitting on a support. And then when your system is stationary, it gives you a 5 centimeter deflection. So this tells you what a K is, because your K is directly related to the deflection. All right, so you can easily calculate your K. And then this machine or this support is sitting on a floor, and a floor is vibrating at very close to the natural frequency. So your R is equal to 1. And then you know that your amplitude Y, YT equals to Y naught cosine omega t. You know that your Y naught is about 0.2 centimeter. You know your zeta is 0.01. And then you know your K. You also know your mass, because your mass is 2,000 Newton divided by G. So you need to calculate the transmitted force due to the base excitation. As we discussed before, so the transmitted force is the inertial force, and then your input is your base excitation. So that's why you already seen this like a moment ago. So that's your force transmissibility. So let's go to the equation on slide number 6. Oops. So let's go back to slide number 6. So you have your M A S over K times YS. That's going to give you a S squared over, what's the ratio again? Okay. That's S squared to omega n zeta S plus omega n squared, and then 2 omega n zeta S plus S squared plus omega n squared. So that's your force transmissibility. And then as you can see here, the K times Y, that gives you a unit of Newton. M times A, that also gives us unit of Newton. So that's your force transmissibility. And then here we want to determine how much force is transmitted. So you want to calculate M times AS. Okay, so what you do is you want to calculate the magnitude of AMAS. So that means you have to calculate the magnitude of your transfer function, multiply the magnitude of your input. So your magnitude of your input is K times Y naught. And then magnitude of your transfer function, you replace S by omega J, and then 2 omega and zeta omega J. And then you calculate the magnitude of this complex number. So that's how you find the magnitude of your transfer function. And then remember, your R is omega over omega n. So you can complete this calculation after class. All right. So whenever you see a problem asking for steady state response, for example, what's the transmitted force at a steady state? That means you have to use a Laplace transform and then use the transfer function. And then just remember you pick the right transfer function, and you also need to identify the correct input and output. I'm going to post the complete solution on online. So if you cannot finish the calculation, it's still fine. Okay, so that concludes all the base excitation stuff. So any questions?
Sorry, do you mind just going back to that omega J stuff real quick? The J is just that complex version of it. That's not like our J from the last exam, right?
What do you mean? I think I
Like
only use J is something like this.
Okay, that's what I thought. Okay, just wanted to double check. All right, thanks.
Yep. Mm-hmm. All right, so after base excitation, we're going to learn another stuff. It's called rotating imbalance. You can actually see a lot of these in practice. I can give you one example. So, for example, your washing machine. So a washing machine is usually a big bucket that is rotating, right? And then, so you're going to load your clothes, and then this clothes is going to rotate together with the washing machine. And then you're going to have some kind of support to hold this bucket in place. You're also going to have dashpot to provide proper damping. And then this entire thing is going to be enclosed in a casing, right? And then the machine is going to sit on a fixed floor. That's the model for a washing machine. So one of the problems we have is, let's give it a coordinate system. Oops. That's bad. Oops. Let's give it a coordinate system X. So the X describes the displacement of your bucket. So we want to minimize X, right? Such that your bucket would never bump into your casing. So that's our design target. Okay. So what we do is we can simplify this washing machine system into a lambda parameter model. So what we have is your M, C, and K. So in this case, your M naught is the mass of dirty clothes. And then your big M is the mass of dirty clothes plus mass of the bucket. Okay, so it actually includes both stuff. So whatever sitting on the mound is going to be the big M. So we also assume that the eccentricity, so let's say this O point is going to be the center of rotation, and then the center of gravity of your dirty clothes, they are at point G. So the distance here is going to be E. So this is called eccentricity. All right. So we also assume that your bucket is rotating counterclockwise in a constant speed of omega r. That's a constant speed. All right. Then let's see what that equation of motion look like. So here you're going to see the benefits of using Lagrange's method. So let's use Lagrange. So L equals to T minus U, right? T is kinetic energy, U is the potential energy. So we can easily write U, and we ignore gravity here. So all your potential energy is due to the deformation of the spring. So we also need to calculate the Rayleigh dissipation function. That's half c times velocity squared. So there's no external force, so no generalized force term. So usually the challenging part is the kinetic energy. So what we should do. So the kinetic energy, we can divide it into two parts, right? The kinetic energy of the big bucket and also the closed. That's your two parts. Your bucket has a total mass of m minus m naught. As I told you before, the m is the total mass, and then m minus m naught is the bucket weight. And then because this bucket is, in this case, is only, we assume it's moving up and down only. So in practice, you're going to have another set of like a mount to support the horizontal, but we're going to simplify the discussion here. All right. So because it's only linear motion, it's going up and down. So that's a linear velocity. How about the clothes? The clothes is half times the total mass times the velocity squared. What is the velocity of your clothes?
Won't that be the, I guess that would be the E value times the mass, correct? Or, sorry, theta times.
Yep, I think you're saying that V equals to the angular speed times the eccentricity E, right?
Yeah, that's my bad, sorry.
Yeah.
Exactly, yes, that's it.
Okay, so let me explain that. So that works fine if your axis is fixed. But then if you look at the clothes, it's rotating, but at the same time, it's moving up and down, right? So that means this velocity is actually relative to the bucket. But then you also have to include the velocity of the bucket relative to the ground, because this velocity is relative to ground. So let me look at these, the velocity at point G. So let's assume this is your theta angle, okay? And then we know that the rotating speed is omega r. So according to what you learned in kinematics or dynamics, the velocity due to rotation is, let's call it v prime. So this is your v prime. But remember that the center point here, oops, that's bad. The center point here is you have a velocity x dot, right? So that means the absolute velocity is so this vector is actually an actual v, the v you want. Make sense? So it's not just v prime. You actually have to consider both v prime and x dot. So how to calculate that? Let me write it out. So you're going to see it more clearly. So that's your v prime. That's your x dot. This angle is theta. And this is perpendicular. This is perpendicular. So according to the geometry relationship, this angle is going to be theta, right? So you create a Cartesian coordinate. That's your x. Oh, too many axes. Let me use a different one. That's using a edge, stands for horizontal. This like P stands for perpendicular. Okay, so what you need to do is you need to do a projection of your V prime. There's your V prime along perpendicular direction. That's your V prime along the horizontal direction. So that means in order to calculate the total V squared is just Vp times x dot square plus Vh prime square. Make sense? That's just how you do a vector summation. So you can write these out. You already know your Vp prime is going to be cosine theta times V prime, which is omega r e. And then your x dot is x dot. And then that's your sine theta omega r e. And then you can plug this back into the original equation. And then you're going to have half m minus m naught x single dot plus half m naught. Then you're going to have all these terms. Cosine theta omega r e plus x dot square plus sine theta omega r e square. And then you can further simplify it. Oops. Let me insert one blank page. So eventually your t would become half m naught. Oops. Half m dot plus m naught x dot cosine theta omega r e plus m naught sine theta square omega r square e square. So that's going to be a kind of kinetic energy terms. And then you can just plug everything back into the Lagrange's equation. And eventually the equation of motion would be something like this. I'm going to provide you the complete derivation after class. So you don't copy a lot of things here. So let me write it down here. All right, so that's the equation of motion. So as you can see, in front of these coefficient, m times angular speed times a displacement, that has a unit of force, unit of Newton. So we usually define these coefficients as out of balance force. So that means this force depends on E, m naught, and omega r. So in order to, so for our washing machine, we have very little control of omega r, but that means if you want to reduce the unbalanced force, you actually want to reduce the total dirty clothes you put in the washing machine, right? That actually makes sense. If you put a full load of clothes in your washing machine, usually it's much noisier. So that's because you have a big m naught that's going to give you a much larger out of balance force. The other thing is actually the eccentricity, your E. So in this case, if you look at your bucket, you actually want your dirty clothes to be evenly distributed on the circumferential, along the circumferential direction, right? If they're evenly distributed, then the center of gravity of these clothes is very close to the center of gravity it's very close to the center of rotation, 0.0. So in this way, so in order to minimize your E, you want to evenly distribute your load. That's actually very important in a lot of scenarios. If you watch closely to your washing machine, and I believe some of the machines actually have a feature to balance the load. So if you press start, the machine actually didn't start immediately. You're gonna see the bucket moving left to the right, and then it says load balancing. So it's actually trying to move your clothes around so that your G can be centered. All right. So the other thing is, so this also applies to your tires. All right. So if you have your tire, you have that's your shaft. Let me put a side view as well. You can simplify your shaft as a spring damper, right? Sometimes you also have a dashpot to absorb the vibration. That's your dashpot. That's your bus. You want to minimize. So while your car tire is rotating in a speed of omega r, you want to make sure the displacement of your car tire along the vertical direction is minimized. All right. So what you need to do is you want to make sure the center of gravity for your tire is close to the center of rotation. So these techniques or these approaches called tire rotation. I believe all of you have heard about that. You're gonna see if you go to some of the auto parts stores, they have these small mesh clamps. You can actually clamp on your tire trims. So what it does is, for example, if your tire is manufactured in a way such that your center of gravity is actually like slightly away from the center of rotation, what you can do is you can bind a small piece of that mass and mount it on this edge to balance that drift. Okay, that entire procedure is called tire balancing, tire rotation. Okay, so that's one thing we have to learn. You have to remember for the unbalanced rotation. So you can minimize the unbalanced force by using a small mass, by adjusting the center of gravity, and by using a lower speed. But if you have no control on this, how do you want to design your M, C, and K? For example, in this case, if you want to design the mount for your washing machine, how do you want to design your K? How do you want to design your C? How do you want to design the total mass of your bucket? All right. So what you do is because we want to minimize the displacement, so we know that the output, it should be X. The input in this case is your out of balance force. Okay, so that means the entire thing on the right. So the transfer function equals to X over out of balance force. Then you can move things around, and then you can easily get M squared CS K over 1. This is your X S over F out of balance. That's the transfer function of interest. As I said, you want to minimize the magnitude of your transfer function. What is the magnitude of your transfer function? You just replace S by omega J, and then you can have 1 over M omega squared K minus plus C omega J. That's a complex number. You want to minimize the amplitude of that complex number. So I have provide a MATLAB code on Blackboard. So here, I already show you some of the equations. So again, remember, we want to achieve a small value of these curves. So we want to design your C, we want to design your K. For K, omega n equals to K over n squared. All right, so let's look at the ideal case. In which case we would like your system to operate in. Again, we use a red line. That's our ideal case, right? And then if you want, you can also define the ideal region. Perhaps somewhere, oh. Oops, yeah. That's your ideal case. And then the ideal region. If you look at it here, this green region, if your washing machine can always work in that region, that's going to be perfect. You don't have, so most of the time, at some extreme cases, you can even get 0 displacement. So how can you, so the first question is, how can we design our system to work on the red line? So if you look at the red line, it's actually high damping, right? We want high zeta values. That means we want high C values. That means you actually want a dashpot that can provide you a lot of damping. So I'm not sure if any of you have ever disassembled a machine, like a washing machine or not. If you look at those dashpots used in the washing machine, they're usually big and heavy. That's because you need a high damping for that system. The other part is, if you want to operate in the ideal region, that means you want your R to be small. Remember that your R is omega over omega n. If you have, that means, first of all, in this case, is omega R. So that means you want your bucket to rotate in a relatively low speed, or you want your omega n to be large. How to achieve that? You want, oh, yeah. So you want a very steep system. So that means when you design a K and C, you want it to be stiff and you want it to be high damping. All right. So any questions related to unbalanced rotation?
I don't have a question on this concept. Although for the homework 1, I was kind of confused a little bit still about. So if we go down right here, guess I'm kind of confused. So the equation that you boxed in, you said that you got from slide number 6. Could we go back up to that for a second here?
Yep.
Where in number 6 do we get that from?
It's this one. You don't see it in omega and, oops, this one.
Oh, okay.
This one is already normalized. So your R is omega over omega n. If you plug omega and omega n back in, then you have the same equation here.
Okay. Okay,
Yeah,
makes
if
sense.
you divide both top and bottom by omega n cubic, I believe, then you actually fourth order, then you're gonna get the equation on slide 6.
Right, and then we replace the S's with the omegas, and then okay.
Yeah.
Gotcha.
Yeah, I'm gonna
Okay.
provide a more detailed solution on Blackboard. Because right now I
Yes,
believe the writing is a little bit confusing.
yeah, that would be
Yeah.
appreciated.
Yeah, definitely. At least one example would be really in detailed. All right.
For sure.
So for the unbalanced rotation, let's look in here. There is an example, homework 4. So we have unbalanced machine problem, and then the mass is rotating around the center O. And we know the stiffness, we know the total mass, and we know the damping ratio. So we already know the out of balance force. Remember that your out of balance force is m times e squared times omega, m times e, m naught times e times omega r squared, right? So that's your out of balance force. That equals to 374 Newton. And then you also know your running speed is in 3000 RPM. So you should convert your omega r into radian per second. The way you do it is like one revolution is 2 pi, and then you have 3000 divided by 1 minute is 6 seconds. So that's give you 50. So eventually you have 100 pi radian per second. That's your rotation speed. And then the first question it asks us is determine the magnitude or the amplitude of the motion due to the out of balance force. So that means you want to find the amplitude of your x. So that means your output is x, your input is out of balance force. You remember that your x over f out, right? So that's in slide, okay, that's in slide 9 right now. Okay. Oops. Actually, where is it? Yep. So that's your slide 9. Let me try to remember the equation. Okay, remember. All right. So your x.
And we're using that x equation, correct?
Yep.
Cool.
We're using the x equation because we want to calculate the x, right? So m r squared 1 minus r squared plus 2 zeta r square root. I read it so fast before I forgot. Okay, so that's our equation. But the problem is we don't know m naught. We only know the entire thing. What you do is you can multiply both the top and bottom by omega r squared, right? Then the first part here is 374. And then we know the total mass, we know the speed omega r, we just calculate that. The total mass is 120. And then always remember your r is the driving speed over the undamped natural frequency. And then your zeta is c over 2 square root mk, right? So once you plug all the system parameters in, you can replace the parameters by numbers and then get the magnitude. That's your part A. Is this clear for the unbalanced rotation?
Right. So we're trying to figure out we're trying to replace the like if this were say like a washing machine, right? The m naught, right? Wait, and so how are we proposing to eliminate that from the equation?
So
never mind. They already give that to us. Never mind. Okay.
Yep. So up to this point, they never tell us what m naught is, what the E is, but they give us the unbalanced force amplitude. So you just multiply everything by omega r squared, then you can replace the entire thing by that force. So for the second part, it actually gives us the m naught. So that says your m naught is 1% of the total mass, or 0.01 m. So it asks for what's the E value. So we already know that m naught E omega r squared equals to 374 Newton. And then your E is just 374 divided by m naught omega r squared. And then you can plug things back in and then get your eccentricity. Right? So that's a washing machine. And let's try and, I'll try to like emphasize the steady state response a little bit more. Oops.
That would be appreciated. Thank you.
Mm-hmm. I think homework 3 is a good example for that. So if you look at this system, there is a base excitation Y exciting a spring mass damper. You want to find out expression. You want to find out how much force is transmitted to the support in steady state. So these sentences give you the parameter of interest, right? So which parameter we want to investigate, we want to study. So we want to investigate how much force is transmitted to the support. So that actually gives us output of transfer function. That means your output should be Ft. As your Y is vibrating, how much force is transmitted to the support. So there is only one component connected to the support, which is spring. So your Ft equals to the spring force, right? So what is the spring force?
Shouldn't that just be Kx?
Yep,
KX.
exactly. So it's just Kx because nothing else is over there. So it's just Kx. And what is your input? So here it's really clear that your input is a base excitation, right? It says that it's a base excitation problem or base motion. So that means your input is Y, T equals to Y times sine omega base T. We want to find the amplitude of Ft at steady state. Because it's at steady state, we just need to find out the transfer function, right? So the transfer function is output Ft divided by input. That's not the best way to write it, but just giving an idea. But your transfer function,
You go there.
yeah, is in S domain. So instead of writing it as a function of t, you should actually write it as function of s. Right? So that's your transfer function you need to find out. So in order to get transfer function, you need to find the system equation, ODE. What is the ODE here? So we need to, the best way is using Newton's method here. So you have a mass is moving up. And then you have your spring force. Let's name it as Fk. You have your damping force, Fc. So what is your Fk? It is minus Kx, right? Is it clear? So that means when you have negative displacement, the spring is pushing the mass upward, right? And
Right, we're
then what is
compressing the spring, correct?
Yeah, because we're compressing it, so it's negative. So your FC is C times Y dot minus X dot, right? If your base is moving faster than your top, that means your dashboard is going to push your mass upward. Okay, so according to Newton's second law, your Fk minus plus Fc is generating a positive acceleration. So if you plug everything back in, you have mx double dot equal to cy dot minus cx dot minus kx. Okay, and then you want to move things. You want to move the output, the response and input to. You want to separate them using the equation symbol. So let's collect all the response to the left-hand side. So you have f cx dot plus kx, because your x is response. And then your excitation is cy dot. So from here, you might not be able to get the transfer function in one shot, but you can easily get a transfer function of xs over ys, right? By doing the Laplace transform on both sides. I'm using a different color. So if you're doing Laplace transform, so m double dot becomes s squared, cs plus k, and then the common term is xs. And then on the right-hand side, you have a CSYS. So based on the Laplace transform, and you move things around, you would have CS over ms squared plus CS plus k. All right, so remember the ultimate target is we need to find out force over the base excitation. But then your force, then you have to go back to this equation. You do Laplace transform on both sides, your FTT becomes FTS, and then your XT becomes XS. If you don't remember that, remember this is a function of time, right? You just do Laplace transform for the time-dependent function. And then there's no time derivative over there. You just replace all the t's by s, then you directly get it. So that means the transfer function of interest is k times xs over ys. And then we already know the x over ys, which is this equation. And then you would have kcs over ms squared plus cs plus k. So that's the transfer function we would like to use. All right, so once you have the transfer function and then your input is harmonic excitation, then your steady state output is relatively easy. So here, you only ask for how much force is transmitted. That means only the amplitude is of interest. Remember that amplitude over amplitude of y is the amplitude of your transfer function. The amplitude of your transfer function is just replace s by omega j, and then you have k c omega j, and then your m omega squared minus plus c omega j plus k. And then if you go back, you're going to see that your excitation is omega b. So that means your omega, your excitation frequency, when you need to find your omega, you need to find the excitation frequency, which is your drive, or sometimes called driving frequency. In this case, it's omega b. And then here you have complex numbers on both top and bottom. So the magnitude, because it's only complex term, so the length of that vector is k c omega. And then on the bottom is k minus m omega squared, the square of the real part plus the square of the imaginary part, sum them together and take a square root. So that's your transfer function you have. In order to find ft amplitude, you just need to multiply these number. Okay, multiply this ratio by this y amplitude. Your y amplitude is big Y. You can directly replace it by big Y. So that's the final solution. How much force is going to be transmitted to the base. I can also ask you, like, what is the phase lag of Ft? Because we already know that your Ft is going to be some kind of amplitude Ft times a harmonic excitation omega, same frequency, but with a certain phase lag. So this phase lag is just the angle of your transfer function. In MATLAB, that's easy. You just use angle, put your transfer function in. So let me summarize this a little bit. When you have a random systems, so in your exam number 2, so most of the system will be, you should have seen most of the system during the class. So that means you can directly go to previous notes and find the transfer function equation you want. I'm also going to give you a random system. You have to start from the scratch. So by reading that problem, you first have to identify what is the input, and then you also need to identify which steady state response we want to calculate, and then pick that thing as your output. If you have output and input, you identify the transfer function you want to find out, and then you go back to use Lagrange's method or Newton's second law to find your ODE, and then do Laplace transform of your ODE to get your transfer function. And then if you have a transfer function, you're going to know the ratio of the steady state amplitude and also the phase of the steady state response. All right. I'm going to post the solutions online by the end of tomorrow. Again, exams will be really similar to these problems. Make sure you understand what's going on. So any questions for me?
Wait, so for a system that we start at scratch, we obviously want to know the input, output, and then you want to know the response of the system in question. So like in the last example, it was the mass, and we were trying to figure out the steady state response of the mass.
Yeah. Are you talking about homework 3?
Yeah.
Yeah. We want to know the steady state response of the force. So that means we want the Ft is your output, but then you find out that your Ft is related to x, or the displacement of the mass.
Right, which we figured out was just going to be kx.
Mm-hmm.
Okay, gotcha.
I can easily draw a lot of systems right now. Like for example, just some random exams. I might just give you one of these as the exam. Like if you have your mass, if you have your K, if you have your C, and that's your C. Oops. C1 and C2. And somebody is pushing it using a Y. T equals to cosine omega t. How much force is transmitted to the base at steady state, right? What's the force amplitude transmitted to the ground at steady state?
That will still be a KX situation, correct? Because it's the spring.
No, because
Oh,
then
but
in
we
this
also need to
case,
count the mass, right?
in this case, actually, you have to consider the damper. Because if you look at the ground, that's Newton's third law, right?
Right.
So
yeah,
how much
there's
force
two.
experienced by the ground is that determined by how much, what are the components connected to the ground? You have spring, you have damper. So that means in this case, your FT is going to be, let me see, let's name it as X, okay? It's KX plus C1 X dot.
All right, that makes sense.
Because the ground force has both this spring force and also the dashboard force.
Okay.
I can give you a lot of examples, like, so that's why I don't believe you use Google or not. So, oops, what's happening here? So for example, it doesn't have to be a force. You can have a mass system. You can have a dashboard, the same thing.
Mm-hmm.
And then something Y applying on the dashboard one. I can use the exact same problem. But then in this case, you're gonna have a pointer. And then your pointer is moving up and down.
And that would be like the displacement in this case.
Yeah, then in this case, your output is displacement. And I can also tell you that if there is a measurement system, instead of measuring the position of your pointer, if it measures the acceleration of your pointer, what's the steady state response of the acceleration? So in that case, your output will be X doubled up.
Right.
So even for the same system, depending on which parameter to analyze, you might end up with different transfer functions. You're going to see these more clearly next lecture when we talk about accelerometers and seismometers. They're actually the same system, but just the way we analyze the output changes the transfer function.
That makes sense.
Mm-hmm. All right. So any more questions?